Even while the night around you appears still, the ground beneath you is carrying you through several motions at once. Earth turns beneath the stars. It follows the sun around a path hundreds of millions of miles long. The sun, carrying Earth and the other planets with it, travels around the center of the Milky Way, and the Milky Way is moving too, not as a solitary island wandering without direction, but as one member of a much larger current of galaxies. Measured against the faint background light left by the early universe, our local group moves at roughly 600 kilometers per second. The Milky Way and Andromeda share this motion with dozens of smaller neighboring galaxies, all traveling together through a landscape shaped by matter spread across distances almost too large to picture. Imagine the universe. Nothing nearby makes this movement obvious. The stars do not stream backward across the sky. The constellations retain their familiar forms. A glass of water beside a bed remains undisturbed. Yet during the few moments needed to notice your next breath, the Milky Way has crossed thousands of kilometers relative to that old background of radiation. For much of the 20th century, astronomers tried to understand where this motion was leading. They measured the recession of distant galaxies and compared it with the smooth expansion expected from the universe as a whole. Most galaxies followed the general outward flow, but their paths were not perfectly even. Some moved a little faster than expected, others moved more slowly. Across a broad region of the nearby universe, many appeared to share a common drift toward the constellations of Centaurus and Norma. The pattern suggested gravity. Somewhere in that direction, matter was altering the motion of galaxies across an immense volume of space. It was not pulling only on the Milky Way. Andromeda moved with us. Nearby groups and clusters participated in the same broad flow. The unseen influence became known as the Great Attractor. The name can make it sound like a single object. It is tempting to imagine a hidden black hole, an enormous star, or one compact body waiting behind the Milky Way. But the Great Attractor is not understood as one isolated object. It is a region where the combined gravity of galaxy clusters, gas, and dark matter helps guide the motion of the surrounding cosmic neighborhood. Part of the difficulty came from its position in our sky. To look toward the Great Attractor, astronomers must look through the crowded plain of the Milky Way. Foreground stars fill the view. Clouds of interstellar dust absorb visible light from distant galaxies. This obscured band became known as the zone of avoidance, not because space beyond it was empty, but because early surveys could not easily see through our own galaxy. Absorption 3. So the first evidence did not arrive as a clear image. It arrived as motion. Galaxies served as markers floating within an invisible gravitational landscape. By measuring their distances, speeds, and departures from ordinary cosmic expansion, astronomers began tracing the slopes and valleys of that landscape without seeing all the matter responsible for shaping it. Later maps would place our galaxy inside a much broader flow called Laniakea, a region containing the Virgo, Hydra, Centaurus, and Norma clusters, along with filaments and neighboring voids. Within that map, the historical Great Attractor lies near a gravitational basin toward which many local galaxy paths converge. Nature 4. But even this is not the complete destination. Structures beyond the Great Attractor also influence our motion, and the largest cosmic currents do not end at one cluster or one boundary drawn on a map. For now, it is enough to notice the movement pace in itself. The Milky Way is not waiting in place beneath the night. It is crossing an unseen terrain carried by gravity toward concentrations of matter, hidden among the stars ahead. To understand how astronomers found an invisible concentration of matter, it helps to begin with something much simpler: the difference between where a galaxy appears to be going and where it would go in a perfectly even universe. On the largest scales, space expands. Distant galaxies are carried away from one another as the space between them grows. The farther away a galaxy is, the faster that expansion usually carries it from us. This broad relation gives astronomers a cosmic pattern, a kind of background current against which smaller motions can be measured. But galaxies do not merely ride that current, they also respond to nearby gravity. A galaxy may be drawn toward a cluster, nudged along a filament, or pushed away from a region containing less matter than average. This additional motion is called peculiar velocity. The word peculiar does not mean strange. It means motion belonging to the galaxy itself, layered on top of the general expansion of the universe. Finding that motion requires two different measurements, the first comes from redshift. When a galaxy moves away, the wavelengths of its light are stretched toward the red end of the spectrum. By measuring this shift, astronomers estimate how quickly the galaxy is receding. For a distant object carried mainly by cosmic expansion, that speed also provides a rough indication of distance. But the estimate is only useful if the galaxy follows the expansion perfectly. If gravity has given it an extra motion, redshift alone cannot reveal the whole story. A galaxy falling toward a massive region may appear to recede more slowly than expected. Another moving in the same direction as the expansion may appear to recede faster. To separate these effects, astronomers need a second distance measurement that does not depend on redshift. That is where the work becomes patient. Galaxies are too remote for ordinary methods. No ruler can be bent across intergalactic space. Instead, astronomers look for features whose true brightness or physical behavior can be estimated. By comparing what those features should look like with what the telescope receives, they can infer distance. Different kinds of galaxies require different tools. Spiral galaxies rotate, and the speed of that rotation is related to their luminosity. Elliptical galaxies contain stars moving in many directions, and the spread of those stellar speeds can also be linked to intrinsic brightness. Other methods use exploding stars, fluctuating patterns of unresolved starlight, or properties of entire galaxy clusters. None of these measurements is perfect. Dust dims light. Galaxies differ from one another. Telescopes introduce small uncertainties. A modest error in distance can produce a large error in the inferred motion. So the early search for the Great Attractor did not depend on one galaxy or one observation. It depended on patterns emerging across many objects. During the 1970s and 1980s, astronomers assembled larger samples of galaxy distances and velocities. They expected random local movements to average out. Instead, a broad shared drift began to appear. Galaxies scattered across a large part of the sky were not behaving as isolated objects. Their peculiar velocities pointed toward the same general region. Some were moving toward it from our side. Others, lying beyond it, appeared to move back in the opposite direction, as though falling toward the same gravitational valley from farther away. The pattern resembled water descending from different slopes toward one low basin, although the galaxies themselves were separated by tens of millions of light years. A group of astronomers, later known informally as the Seven Samurai, played an important role in making this pattern visible. They studied the distances and motions of hundreds of elliptical galaxies. Their results suggested that a large volume of the nearby universe was streaming toward a hidden concentration in the southern sky. The influence seemed far greater than that of the Virgo cluster alone. Virgo is the nearest large galaxy cluster to the local group, and its gravity does affect our surroundings. It contains thousands of galaxies and lies a little more than 50 million light-years away. For a time, it was natural to think that much of our motion could be explained by falling toward Virgo, yet the measurements did not align completely with Virgo. The direction was offset, the scale was larger. The flow continued across regions too broad to be governed by one nearby cluster. Something beyond Virgo appeared to be contributing. The cosmic microwave background provided another clue. This radiation reaches us from every direction and comes from a time when the universe was very young. After accounting for tiny natural variations, it forms one of the closest things astronomy has to a reference frame for large-scale motion. The background is not measured at exactly the same temperature in every direction. It appears slightly warmer in one part of the sky and slightly cooler in the opposite direction. The difference is produced mainly by our motion. As the local group travels through the surrounding universe, we move into the ancient radiation on one side and away from it on the other. It is similar to the way rain appears to strike the front windshield of a moving car more directly than the rear window, even when the rain itself is falling evenly. From this dipole pattern, astronomers determined that the local group moves at roughly 600 kilometers per second relative to the cosmic background. That speed is not directed straight toward the center of the Milky Way. It is not explained only by our orbit around the Sun or the Sun's orbit within the galaxy. Those smaller motions can be removed from the calculation. What remains is the motion of our entire galactic neighborhood. The direction pointed broadly toward the same hidden part of the sky indicated by galaxy surveys. This agreement mattered. One method studied light left over from the early universe. Another compared the distances and redshifts of nearby galaxies. Each contained different uncertainties, yet both suggested that the local group was participating in a larger gravitational flow. Still, the map was incomplete. The most important region lay close to the plane of the Milky Way, where visible light surveys lost their reach. Dense fields of foreground stars, confused images, dust absorbed the blue and visible glow of distant galaxies. The farther astronomers looked into that band, the more their map seemed to dissolve. The missing area was not small. It wrapped around the sky like a broad, irregular belt. Early catalogues showed fewer galaxies there, not because galaxies were truly absent, but because our own galaxy stood in front of them. For observers inside the Milky Way, this is an unavoidable condition. We see the universe from within a luminous disk filled with stars, gas, and dust. Looking above or below the disk opens a relatively clear view into deep space. Looking along it means seeing through thousands of light years of our own galactic material before any distant cluster can be studied. The Great Attractor lay close to that difficult line of sight. Its presence was inferred before its structure could be seen clearly. Gravity had revealed the rough shape of the answer, while light still concealed the objects producing it. This was one of the quieter achievements of modern astronomy. The first map was not a picture of matter. It was a map of consequences. Galaxies changed their speeds. The microwave background showed a directional imbalance. Clustersurns failed to match a perfectly smooth expansion. From those small departures, astronomers reconstructed the pull of structures hidden beyond the crowded foreground of the Milky Way. The universe had left no signpost naming the destination. It had only allowed the surrounding galaxies to lean toward it. The Milky Way hides distant galaxies most effectively in visible light. That is the light human eyes know best, and it is also the range used by many of the earliest photographic sky surveys. In directions away from the galactic plane, those surveys revealed fields crowded with remote galaxies. Near the plane, the fields changed. Foreground stars multiplied, while the light of objects beyond them faded behind layers of dust. The universe did not end at that boundary. Only one way of seeing it did. Interstellar dust is made of grains small enough to remain suspended between the stars. Some contain silicate minerals, others are rich in carbon. They absorb and scatter shorter wavelengths more readily than longer ones, which means blue and visible light crossing the Milky Way can be weakened before it reaches a telescope on Earth. A distant galaxy behind the galactic plane may still contain hundreds of billions of stars. Yet by the time their combined light passes through enough foreground material, the galaxy can disappear from an ordinary image. The effect is uneven. The Milky Way's dust does not form a smooth curtain. It gathers into clouds, lanes, and filaments. One narrow sightline may offer a partial opening, while a nearby direction becomes nearly opaque. This turns the zone of avoidance into a shifting patchwork rather than a clean band with simple edges. For early astronomers, it created a map with a missing middle. Galaxies appeared above the Milky Way, and below it, groups and clusters could be traced toward the obscured zone, then seemed to stop. Structures that might have continued across the sky were broken into separate pieces because the connecting region could not be observed. The Great Attractor lay within one of the most difficult parts of that hidden territory. The evidence from galaxy motions suggested that considerable mass was present there. But knowing that something influences its surroundings is different from seeing its contents. Astronomers needed forms of light that could pass through the foreground more successfully. One of those forms was infrared. Infrared wavelengths are longer than visible wavelengths. They are less strongly scattered by many kinds of interstellar dust, allowing telescopes to peer deeper into regions where visible light surveys struggle. A galaxy dimmed almost beyond recognition in a blue photograph may become detectable in the near-infrared glow of its older stars. Infrared surveys began filling the missing band with faint points and dense spaceships. Some belonged to stars within the Milky Way. Others were galaxies far behind it. Separating the two required careful analysis because the foreground remained crowded. Astronomers compared colors, shapes, spectra, and motions, gradually distinguishing nearby stars from entire stellar systems lying millions of light years farther away. Radio astronomy opened another route. Cold hydrogen gas emits radiation at a wavelength of 21 centimeters. This radio signal can travel through the dust that blocks visible light. Spiral galaxies rich in hydrogen can therefore announce their presence even when their stars remain hidden. A radio telescope does not need to see the spiral arms directly. It can detect the hydrogen moving within them. The frequency of the signal reveals a galaxy's redshift, while its distribution and width carry information about motion and rotation. By scanning the zone of avoidance, radio surveys uncovered galaxies that had been absent from optical catalogues. The hidden sky began to acquire depth. What had looked like a blank region became populated by galaxies at different distances, moving at different speeds, arranged into groups and larger concentrations. Filaments continued through the obscured band. Dense regions emerged where older maps had shown almost nothing. X-rays provided a third view, one especially useful for finding massive galaxy clusters. A rich cluster is not made only of galaxies. Much of its ordinary matter can exist as thin gas spread through the space between them. The gas is heated to temperatures of millions of degrees as it falls into the cluster's gravitational field and is compressed. At those temperatures, it radiates strongly in X-rays. Dust that blocks visible starlight does not erase this high-energy signal in the same way. An X-ray observatory can detect the glow of hot intracluster gas and reveal a large concentration of matter behind the Milky Way. The shape and brightness of the emission help astronomers to make the scale of the cluster, while spectra provide clues to the gas temperature, and composition. In the direction of the Great Attractor, these methods brought one cluster into particular focus. It is known as the Norma Cluster, or Abell 3627. The cluster lies roughly 200 million light-years from Earth, within the constellation Norma as projected on the sky. It contains hundreds of galaxies gathered in a deep gravitational well. Many are large elliptical systems dominated by older stars. Others show signs of interaction as they move through a dense environment filled with galaxies and hot gas. The Norma Cluster is among the most massive nearby clusters. Its galaxies do not sit motionless inside it. They travel through the cluster at high speeds, their paths governed by the combined gravity of visible matter and dark matter. The hot gas between them shines in X-rays. Radio observations reveal active galaxies and distorted structures shaped by motion, pressure, and collision. Here, at last, was a visible part of the mass concentration that earlier surveys had inferred from movement alone. But Norma was not a single answer to every question. It was an important landmark within a larger region. The historical idea of the Great Attractor emerged before astronomers could map all the structures in that direction. As observations improved, the picture became less like one concealed object and more like a network of clusters, groups, filaments, and dark matter concentrations. Norma marked one dense node in that network, close to the region where reconstructed galaxy flows appeared to converge. The distinction matters because gravity does not require a single center with a sharp edge. Every concentration of matter contributes. A nearby group exerts one influence. A rich cluster adds another. Long filaments contain galaxies, gas, and dark matter, distributed across tens of millions of light-years. More distant concentrations also pull. though their effect weakens with distance and combines with everything between. The local group's motion is the result of this full landscape. Virgo contributes. The Hydra and Centaurus regions contribute. The Norma Cluster contributes. Structures farther away, including the Shapley Concentration, also shape the broader flow. At the same time, nearby regions with less matter than average affect the motion from the opposite direction. An underdense region does not push galaxies through a new force. Its influence appears because there is less gravity pulling from that side. If matter is distributed unevenly, the stronger attraction from dense regions is not fully balanced. A galaxy then accelerates toward the side containing more mass. This means our motion may be understood partly as attraction toward crowded regions and partly as departure from emptier ones. The cosmic landscape is shaped by both. Around the local group, one important underdense region is commonly called the local void. It lies beside our galactic neighborhood and contains fewer galaxies than the cosmic average. The local group's motion reflects not only the pull of concentrations toward the Great Attractor region, but also the imbalance created by this nearby emptiness. The picture is more subtle than an arrow pointing from the Milky Way toward one destination. It resembles a leaf carried where several currents meet. One current may be nearby and strong. Another may be broad and distant. A third may arise because water is absent from one side of the flow. The leaf follows the combined result without needing to know where one influence ends and another begins. Galaxies behave in a similar way, though the currents are gravitational and the motion unfolds across billions of years. As surveys looked through the zone of avoidance, they also corrected an old visual illusion. The apparent emptiness of that band had always belonged to the observer. From another galaxy located far above the Milky Way's disk, the hidden region would not be hidden at all. An astronomer there might see the Norma Cluster directly, while finding some other part of the universe concealed behind the plane of their own galaxy. Every cosmic map is made from somewhere. Our position gives us a close view of the Milky Way's stars, spiral structure, gas, and dust. It also places those same features in front of the wider universe. The galaxy that allows us to exist becomes part of the obstacle when we try to see beyond it. There is a familiar human scale within that problem. For much of history, people navigated by visible stars. Their positions could be remembered, shared, and passed between generations. A star hidden by a cloud was understood to remain present even when it could not be seen. Its absence from view did not mean its removal from the sky. Modern astronomers worked with a similar patience toward the zone of avoidance. They trusted the motions around it. They changed wavelengths. They built receivers sensitive to radio signals, infrared glow, and X-rays. They allowed the hidden structures to reveal themselves through whatever form of light could complete the journey, and gradually, the blank portion of the map became a place. It contained the Norma Cluster and neighboring structures. It carried the continuation of filaments seen on either side of the Milky Way. It held enough matter to help explain why nearby galaxies shared a common motion. Yet the deeper the region became, the less the Great Attractor resembled the name first given to it. There was no single concealed engine. There was a gravitational watershed assembled from many visible and invisible parts, with the Norma Cluster standing near one of its deepest mapped regions. What pulled the Milky Way was not a point waiting at the end of space, but the uneven architecture of space itself. The obscuring dust had hidden the galaxies. It had never hidden their gravity. Beyond the Norma Cluster, the gravitational map continues to deepen. The first generations of Great Attractor studies were limited by the reach of available surveys. Astronomers could trace the motions of nearby galaxies and identify a broad convergence toward the Centaurus and Norma region. But the universe does not end at the distance where a telescope survey becomes incomplete. Matter continues beyond it, and that more distant matter also contributes to the motion measured closer to home. As observations extended farther into space, another major concentration came into view. It is called the Shapley Supercluster, or more carefully, the Shapley Concentration. It lies several hundred million light-years away, in roughly the same broad part of the sky. as the Great Attractor, though farther beyond it. The region contains numerous galaxy clusters packed into a large overdensity. Some of those clusters are rich systems holding hundreds or thousands of galaxies. Between them are filaments, smaller groups, hot gas, and dark matter spread across an immense volume. The name comes from astronomer Harlow Shapley, who noticed an unusual excess of galaxies in that direction during the early 20th century. At the time, the scale of the structure could not be understood in modern terms. The distances were uncertain. The expansion of the universe had only recently entered astronomy. Galaxies themselves were still being recognized as systems outside the Milky Way. What appeared on photographic plates as a crowded patch of faint light would later become one of the most massive known concentrations in the nearby universe. Shapley does not replace the Great Attractor, it changes the meaning of it. The Great Attractor was originally defined through the observed motion of galaxies in the local universe. It described the direction and scale of a gravitational flow. The Norma Cluster and nearby structures helped explain part of that flow. But once the Shapley Concentration was mapped, astronomers had to consider whether the local motion was being influenced by mass much farther away. Gravity does not stop at the edge of a supercluster. Its influence weakens with distance, but a sufficiently large concentration can still matter. A nearby cluster may exert a strong pull because it is close. A more distant concentration may contribute because it contains far more mass. The resulting motion depends on both the amount of matter and the geometry of its distribution. This makes the path of the Milky Way difficult to reduce to one source. Imagine standing on a broad, nearly level surface where the slopes are too slight to see. A small depression nearby may draw water in one direction. A deeper basin farther away may tilt the surface more gradually across a much larger area. If both are present, the water follows the combined descent. The galaxies around us move through a landscape like this, though the surface is not made of ground and the descent is not caused by ordinary height. It is a map of gravitational potential shaped by visible matter, dark matter, and regions where matter is missing. The Great Attractor region forms one part of the slope. The Shapley Concentration forms another. Astronomers study their relative influence by reconstructing peculiar velocities over larger and larger distances. They compare measured galaxy motions with models of the matter distribution. They use redshift surveys to map clusters and filaments. They estimate mass from galaxy counts, X-ray emission, gravitational effects, and the motions of galaxies inside clusters. The task is delicate because mass is not distributed only where light is bright. A galaxy cluster contains stars, but the stars are only part of its total matter. Hot gas can contain more ordinary matter than all the stars combined. Dark matter contributes still more, shaping the cluster's gravity without emitting light of its own. A region that looks moderately bright may therefore hold a deep gravitational well. Another region filled with luminous galaxies may be spread so broadly that its pull is less concentrated. Astronomers must translate a map of light into a map of mass, and the two are related without being identical. This is one reason the Great Attractor remained difficult to define. It was never a clean object with a visible boundary. It was an inferred center of flow within a survey volume. As the survey volume expanded, the reconstructed center could shift. New clusters entered the calculation. Hidden galaxies were added, corrections improved. The larger gravitational context became clearer. The term remained useful, but it no longer carried the same simplicity. In some of the local groups, motion appears connected to structures in the nearby universe, including Virgo and the Great Attractor region. Another portion reflects the influence of more distant concentrations, such as Shapley. Still another part arises from underdense regions, including the local void. The final velocity is a sum. There is no need for one dominant hand moving the Milky Way. The motion can emerge from many small and large gravitational imbalances acting over time. A galaxy responds to the entire distribution around it, not only to the most famous cluster in a catalogue. This broader view also helps explain why the word attractor can be misleading. In ordinary language, an attractor sounds like a destination. It suggests a place toward which everything is falling, and where everything will eventually arrive. That is not quite what happens here. The universe is expanding. Galaxy groups and clusters have their own local motions within that expansion. Structures evolve. Matter flows along filaments. Some regions are gravitationally bound, while others are separating too quickly for their mutual attraction to overcome cosmic expansion. A present-day velocity vector does not guarantee a future arrival at the point it currently indicates. The Milky Way may be moving toward a region of higher density, but that region is also moving. The large-scale pattern changes as structures continue to evolve. The word attractor describes a flow field more accurately than it describes a final destination. The distinction becomes clearer when considering the scale involved. The Milky Way belongs to the local group. The local group contains the Milky Way, Andromeda, the Triangulum galaxy, and many smaller galaxies. Within this group, gravity is strong enough to bind the system. The Milky Way and Andromeda are approaching one another, and their future interaction is governed mainly by the gravity of the local group itself. The local group lies near the edge of the Virgo cluster's wider neighborhood. Virgo is much larger, but the local group is not simply falling straight into its center. Our motion includes sideways components and the influence of other nearby structures. The geometry is three-dimensional and uneven. Beyond Virgo are still larger arrangements. Clusters gather into filaments and walls. Voids occupy the spaces between. Dense regions are connected rather than isolated. A line drawn toward the Great Attractor passes through one part of this network, then continues toward larger concentrations farther away. From Earth, these structures appear projected onto the same general region of sky. That can create the illusion that they are stacked into one object, but they lie at different distances. The Centaurus cluster is nearer than the Norma Cluster. The Norma Cluster is nearer than the main Shapley Concentration. Each belongs to a different part of the gravitational terrain, though their effects can overlap from our point of view. The depth is hidden inside the direction. Only distance measurements separate the layers. This is why redshift surveys became so important. A flat image of the sky shows angular position. A redshift survey adds a third dimension by estimating how far away each galaxy lies. The result is not a photograph in the ordinary sense. It is a spatial map built from light stretched by cosmic expansion. In such maps, galaxies do not fill space evenly. They form threads, sheets, knots, and arcs around large empty regions. Clusters appear where several filaments meet. The Great Attractor region becomes one crowded intersection. Shapley appears as another, larger and farther away. Between them, the cosmic web carries matter across distances that take light hundreds of millions of years to cross. The Milky Way occupies one small strand within that web. Its motion is not separate from the pattern, it is part of the pattern. When astronomers measure our velocity relative to the cosmic microwave background, they are detecting the local result of a much wider arrangement. Every cluster contributes a small gravitational instruction. Every void removes a balancing influence. Over cosmic time, those differences become motion. A person resting beneath the night sky experiences none of this as movement. The body feels Earth's surface. The room holds its shape. The stars rise and set with familiar regularity. The larger velocity remains hidden because everything nearby shares it. The local group moves together. The Milky Way does not leave the Sun behind. The Sun does not leave Earth behind. Nearby galaxies participate in much of the same broad drift. Motion becomes noticeable only when compared with something outside the moving system, such as the ancient microwave background or galaxies following a different local flow. There is an older pattern here, one that has guided every attempt to understand motion. Without a reference, movement can disappear. A ship crossing calm water feels motionless from its deck. The mast, the ropes, and the people aboard all travel together. Only the coastline reveals the passage. In the same way, the cosmic microwave background provides a distant reference against which the motion of our galactic neighborhood becomes measurable. The background is not a fixed wall surrounding the universe. It is radiation filling space, arriving from a time before stars and galaxies had formed. Its dipole pattern allows astronomers to determine how we move relative to that early cosmic frame. Against it, the local group is clearly in motion, but the question of why cannot be answered by one cluster alone. The Great Attractor opened the investigation. Norma gave the hidden region a visible center of mass. Shapley widened the scale. Voids revealed that absence also matters. Each discovery made the gravitational landscape more complete and the original name less literal. What first seemed like a concealed object became a lesson in cosmic structure. Galaxies move because the universe is uneven. Matter gathers in some places and thins in others. The imbalance creates slopes that cannot be seen directly. Over millions and billions of years, galaxies follow those slopes, carrying stars, planets, and entire histories with them. The Milky Way is following one now. It is not moving toward a single answer. It is moving through a field of many answers, layered one beyond another in the same southern sky. Once astronomers began treating galaxy motion as a map, the Great Attractor became part of something larger. The change was not simply a matter of finding more galaxies. It came from asking a different question. Instead of beginning with visible clusters and deciding which ones belong together, researchers asked where galaxies would travel if their measured motions were followed through the surrounding gravitational field. The result was a new way of defining our cosmic neighborhood, based not only on where matter appears, but on how matter flows. That approach led to Laniakea. The name was introduced in 2014 for the broad basin of galaxy motions that contains the Milky Way. It comes from Hawaiian language and carries the sense of an immense or open heaven, a fitting name for a structure so large that ordinary ideas of location begin to lose their usefulness. Laniakea is not a cluster in the way Virgo or Norma is a cluster. A galaxy cluster is a relatively dense, gravitationally connected system. Its member galaxies move with shared potential. Hot gas fills the spaces between them. Dark matter provides much of the mass that holds the system together. Laniakea is a different kind of object. It is a region of the cosmic web defined by a pattern of inward-flowing, peculiar velocities. After the general expansion of the universe and longer range motion are accounted for, galaxies within this region tend to follow paths toward a shared gravitational basin near the historical Great Attractor. The distinction may seem small, but it changes the map. Earlier superclusters were often identified by looking for connected concentrations of galaxies. Astronomers traced clusters, walls, and filaments, then drew boundaries around the crowded parts. The difficulty was that the cosmic web is continuous. One filament joins another. Dense regions merge gradually into less dense regions. There is rarely a visible edge where one supercluster clearly ends and another begins. Velocity offered another kind of boundary. Consider rain falling across a mountain range. Water landing on one side of a ridge may eventually enter one river system. Water landing only a short distance away on the opposite side may flow toward another. The ridge acts as a watershed. It separates two drainage basins, even though the ground itself remains continuous. The researchers mapping Laniakea applied a similar idea to galaxy motion. They reconstructed a three-dimensional velocity field from measured distances and redshifts. At many points in that field, they calculated the direction matter would tend to move after the smooth cosmic expansion was removed. They then traced imaginary streamlines through the field. Some streamlines converged toward one basin, others moved toward neighboring concentrations, including the broad Perseus-Pisces region. Between those patterns lay a surface where the directions divided, a cosmic watershed separating one flow basin from another. The Milky Way fell inside the basin leading toward the Great Attractor region. So did the Virgo cluster, the Hydra Centaurus structures, the Pavo Indus region, and many other groups and filaments that had once been described as separate superclusters. Under the velocity-based definition, they became parts of one larger domain. That domain spans roughly 500 million light-years. Within it are on the order of 100,000 large galaxies, along with smaller galaxies too faint to catalogue completely, enormous quantities of gas, and a far greater share of dark matter than visible starlight alone would suggest. Its total mass is estimated at about 100 quadrillion times the mass of the Sun. The numbers describe scale, but not shape. Laniakea is not a sphere. It is irregular, branching, and deeply connected to the surrounding cosmic web. Dense knots sit where clusters have formed. Long filaments stretch between them. Sheets of galaxies curve around voids. The Milky Way lies far from the central concentration, near one of the outer reaches of the mapped flow basin. Our position is closer to a tributary than to the mouth of a river. The local group belongs to a chain of structures leading toward Virgo. Virgo, in turn, participates in a larger flow through the supercluster. Farther along, the reconstructed paths descend toward the region near Norma and the Great Attractor. The entire arrangement cannot be seen in one image. No telescope can step outside the universe and photograph Laniakea from a distance. Every map is reconstructed from observations made within it. Astronomers measure galaxies from Earth, estimate their positions in 3 dimensions, correct for incomplete coverage, and infer the velocity field from data that contain uncertainty. The resulting picture is part observation and part reconstruction. That does not make it arbitrary. The known galaxies provide anchors. Their measured redshifts give recession velocities. Independent distance indicators reveal departures from smooth expansion. Statistical methods then estimate the most likely velocity and density fields between the measured points. Where the data are plentiful, the reconstruction is more secure. Where the Milky Way obscures the background, or where distances become harder to measure, the uncertainty grows. Different plausible versions of the map can shift a boundary or soften the location of an attractor. Modern studies increasingly describe these structures in probabilistic terms, acknowledging that a galaxy near a watershed may not belong to one basin with perfect certainty. The cosmic map has edges made from confidence rather than walls. This is appropriate for a universe whose large structures blend into one another. A supercluster does not carry a border visible in space. A galaxy crossing from one inferred flow basin into another would not encounter a change in color, temperature, or texture. The boundary exists in the direction of motion, just as a watershed on Earth may pass through a field without any sign that rain landing on either side will reach different seas. Laniakea also does not mean that everything inside it is gravitationally bound. This is another important difference between a cluster and a supercluster. Within the local group, gravity dominates strongly enough that the Milky Way, Andromeda, and their smaller companions remain connected despite cosmic expansion. Within the central regions of a rich cluster, galaxies and hot gas are similarly held together. Across hundreds of millions of light years, the situation changes. The expansion of the universe matters more. Many parts of Laniakea are not bound into one permanent system. The present flow pattern records the gravitational landscape of our era, but it does not guarantee that all of these galaxies will eventually gather near the Great Attractor. Some structures will continue separating over immense spans of time. Clusters already bound may remain together. Individual groups may merge internally. But the larger supercluster is not one object preparing to collapse into a single final cluster. Cosmic expansion and the accelerating behavior attributed to dark energy prevent that simple future. Laniakea is therefore a description of relationship in the present universe. It tells us which way galaxies are moving now after broad motions are removed. It reveals a basin in the local velocity field. It gives the Milky Way a larger address, though not an eternal one. The address begins close to home. Earth moves with the Sun. The Sun moves within the Milky Way. The Milky Way belongs to the local group. The local group sits along the outskirts of the Virgo-related flow. That flow becomes part of Laniakea, with its streamlines descending toward the Great Attractor region. Beyond Laniakea, the motion continues within larger patterns that are still being mapped. Each level is real, but each is defined differently. A planet is held to a star. A star is held within a galaxy. A galaxy may be held within a group. A group may occupy a supercluster flow basin without being permanently bound to every other member of that basin. The word belongs changes meaning as the scale widens. At smaller scales, it often describes a durable gravitational connection. At larger scales, it may describe a temporary shared motion within an evolving field. This is one reason maps of the universe can appear to disagree. One map may emphasize where galaxies are densely concentrated. Another may emphasize which clusters are connected by filaments. A third may show the direction of peculiar velocities. A fourth may divide space according to gravitational basins. The maps are not always competing. They may be describing different properties of the structure. A city can be divided by rivers, elevation, postal districts, roads, or patterns of movement. Each map serves a purpose. None alone contains the full experience of the city. The nearby universe is similar. A density map makes the cosmic web visible. A velocity map shows how matter responds to that web. A flow basin marks where the responses converge. Laniakea emerged from combining these ideas into a coherent picture. The map also changed the scale of the Great Attractor. Within the Laniakea reconstruction, the Great Attractor is not an isolated mystery beyond our neighborhood. It is the lower region of the same gravitational terrain that contains us. The Milky Way does not stand outside the structure, looking inward toward a distant influence. We are already inside the flow. The motion is shared by galaxies spread across a wide volume, each occupying its own place along a route shaped by surrounding matter. Some paths pass through clusters, others trace filaments. Others begin near voids, where the absence of balanced attraction redirects the motion toward denser regions. If these paths could be seen, they would form a network of curved lines. They would not all point directly toward Norma. Nearby gravity bends them. Filaments guide them. Some paths converge, while neighboring ones separate across a watershed. The overall pattern resembles the branching of rivers, but there is no water and no fixed ground beneath the flow. The landscape is made from gravity. The travelers are galaxies, and the map itself evolves as matter moves. There is a generational thread in how this picture was assembled. Early sky catalogues recorded positions, later surveys added redshifts, distance measurements revealed peculiar velocities, radio and infrared observations filled portions of the obscured sky. Computers reconstructed fields too complex to calculate by hand. Visualization turned thousands of measurements into streamlines that human eyes could follow. No single observer saw Laniakea. It emerged from many kinds of attention, extended across decades and shared between telescopes, instruments, institutions, and researchers. Each measurement carried only a small portion of the final structure. Together, they allowed the local universe to be viewed not as a collection of separate islands, but as a connected field of motion. That field continues through the room around you. Gravity from distant structures is weak at any one moment. It does not disturb the body or alter the objects nearby in a noticeable way. Yet it has acted across enough time to shape the movement of the entire local group. The influence does not need to feel strong, it only needs to persist. Across millions of years, a slight acceleration becomes a meaningful velocity. Across billions, it helps carry galaxies along the filaments and toward the deeper regions of the web. Laniakea is the name given to one part of that long response. It contains our galaxy, though it is far larger than any place we can visit. It has a boundary, though nothing marks it. It has a center of flow, though not a single central object. It has a present shape, though that shape will not remain unchanged forever. And somewhere near its outer reaches, the Milky Way continues along one narrow tributary, carrying the solar system through a gravitational basin, too large to see and too gradual to feel. There is another layer beneath the map of galaxy motion, one that cannot be photographed directly. Most of the matter shaping the Great Attractor region does not shine. The galaxies provide visible markers. Their stars trace the places where matter has gathered densely enough for gas to cool, collapse, and form luminous systems. Hot plasma between galaxies adds another observable component. Yet, when astronomers total the stars and gas, the result is not enough to explain the speeds of galaxies inside clusters, or the larger gravitational landscape guiding their motion. The missing share is called dark matter. Dark matter does not appear dark because it absorbs visible light like dust. As far as observations show, it neither emits nor reflects enough electromagnetic radiation to be detected in the ordinary way. Its presence is inferred from gravity, from the movement of objects that can be seen, and from the bending of light passing through space. This makes it especially important to the story of the Great Attractor. The Great Attractor first rescues through gravitational consequences rather than through a clear image. Galaxies leaned toward a region partly hidden by the Milky Way. Their motions revealed that more mass was present than early catalogues could account for. Some of that unseen mass belonged to obscured galaxies and hot gas. Much more was expected to be dark matter. Within a cluster such as Norma, galaxies move too quickly to be held together by visible material alone. If the cluster contained only the matter shining through telescopes, many of its galaxies would have enough speed to escape. Instead, they remain confined within a shared gravitational well. The simplest explanation is that the cluster sits inside a much larger halo of invisible matter. The halo is not a shell with a sharp outer surface. It is a broad distribution whose density increases toward the cluster's central regions and gradually thins with distance. Galaxies and gas occupy this gravitational framework. Their motions respond to the total mass, not only to the portions that produce light. Dark matter also links clusters into the larger cosmic web. In the early universe, matter was distributed almost evenly, with small variations in density. Regions containing slightly more matter exerted a little more gravity. Over time, they drew in additional material and became denser. Dark matter, unaffected by pressure from radiation in the same way as ordinary gas, began gathering into an underlying network. Ordinary matter followed. Gas fell into the dark matter wells. It heated, cooled, and formed stars. Galaxies appeared along the filaments. Clusters developed where several filaments met. Voids grew emptier as matter moved toward the surrounding walls and strands. The luminous universe formed within an older invisible framework. This is why maps made from galaxies reveal the cosmic web so clearly. The galaxies do not create the entire structure by themselves. They illuminate selected portions of a much larger distribution. Near the Great Attractor, dark matter contributes to every major gravitational feature. It surrounds individual galaxies. It dominates the mass of galaxy groups. It forms extensive halos around rich clusters. It stretches through filaments between those clusters. The movement of the Milky Way reflects the combined pull of this invisible architecture, along with the stars and gas embedded within it. Dark matter does not require the Great Attractor to be one immense hidden object. A widespread distribution can generate the observed flow. Several clusters, connected by filaments and surrounded by additional matter, can create a broad gravitational basin. The center of that basin may lie near a dense cluster, but its influence comes from the whole surrounding landscape. Astronomers estimate this landscape in several ways. One method uses the motions of galaxies inside clusters. A galaxy traveling through a cluster carries information about the cluster's gravity. By measuring the speeds of many members and studying how those speeds vary with position, astronomers estimate how much mass must be present to keep the system together. Another method studies hot gas. Gas falling into a cluster's gravitational well is compressed and heated. Its X-ray temperature reflects the depth of that well. Hotter gas generally requires a more massive cluster to confine it. The distribution of the X-ray glow also shows how the gas settles within the cluster's gravitational field. A third method uses gravitational lensing. Mass bends spaces, and light follows the curved geometry. When a distant galaxy lies behind a massive cluster, its light can be distorted before reaching Earth. The background galaxy may appear stretched into an arc, multiplied into several images, or subtly reshaped. The amount of distortion depends on the total mass along the line of sight. It does not matter whether that mass is luminous. By mapping the changes in many background galaxies, astronomers reconstruct the cluster's mass distribution, including the dark component. Strong lensing reveals dramatic arcs near dense central regions. Weak lensing produces smaller distortions across a wider field, detectable only by combining measurements from many galaxies. Each method has different uncertainties. Galaxy motions can be complicated by mergers and uneven orbits. X gas may be disturbed rather than fully settled. Lensing combines all matter projected along the line of sight. When the methods broadly agree, confidence in the mass estimate becomes stronger. In the region of the Great Attractor, the geometry makes every method harder. The plane of the Milky Way adds foreground stars and dust. Some background galaxies needed for lensing studies are obscured. Radio and infrared surveys must work through crowded fields. Cluster membership can be difficult to establish when many unrelated objects overlap in the same direction. Even so, the hidden mass does not remain completely inaccessible. Its effects accumulate. A single galaxy velocity may be uncertain. Thousands of velocities reveal a flow. One distorted background image may be ambiguous. A field of distortions reveals a gravitational pattern. One cluster may not explain the motion of the local group. A network of clusters, filaments, and voids can. This is how astronomy approaches matter that cannot be held, illuminated, or observed directly. It studies what the matter does. The method is not unique to dark matter. Neptune was predicted from the altered orbit of Uranus before it was seen. Some black holes were inferred from the movement of nearby stars or gas, before their surroundings were imaged in detail. The Great Attractor was named from galaxy motion before the hidden region could be surveyed fully. Gravity leaves traces. Those traces are often slow and geometric. An orbit bends, a beam of light curves. A galaxy moves a little faster than cosmic expansion predicts. None of these changes needs to be dramatic. Precision turns them into evidence. Dark matter remains scientifically unresolved in another sense. Its gravitational behavior is well established across many kinds of observation, but its physical identity is still unknown. It may consist of particles not yet detected directly. Many candidates have been proposed, and experiments continue to search for interactions beyond gravity. So far, no single particle explanation has been confirmed. That uncertainty does not erase the gravitational evidence. It separates two questions. The first asks whether additional unseen mass is required to explain galaxies, clusters, lensing, and cosmic structure. The evidence supporting that conclusion is extensive. The second asks what the unseen matter is made of. That question remains open. In a sleep-compatible view of the cosmos, uncertainty does not need to become suspense. It can remain what it is, a boundary around present knowledge. Astronomers can map dark matter more confidently than they can identify its substance. They can estimate where it gathers and how strongly it bends light. They can include it in simulations that reproduce the broad architecture of the cosmic web. Yet the material itself has not entered a laboratory instrument in a way that settles its nature. The Great Attractor sits within that wider unknown. Its gravity can be reconstructed without every component being understood at the microscopic level. The Milky Way responds to the mass whether or not human beings know the particles carrying it. This creates a strange contrast between scale and knowledge. Across hundreds of millions of light years, dark matter helps organize galaxies into filaments and clusters. Its effects are visible in the movement of immense structures. But at the smallest level, the identity of the material remains concealed. The largest map depends on a missing name. Cosmological simulations show why the invisible matter so much. Researchers begin with a young universe containing small density variations. They include gravity, expansion, dark matter, gas, radiation, and the physical processes needed for stars and galaxies to form. Over billions of years, the denser regions grow. Filaments emerge. Clusters gather at their intersections. Voids widen between them. The result resembles the large-scale pattern found in surveys. Without a dominant dark component, matter does not assemble in the same way or on the same schedule. The observed universe, with mature galaxies and clusters appearing where they do, is difficult to reproduce. The Great Attractor is therefore not merely a local curiosity. It is one expression of the same process that built structure throughout the cosmos. A slight unevenness in the early universe, became a deeper gravitational valley. Dark matter gathered first, gas followed, galaxies formed, clusters grew. Neighboring systems began moving in response to the developing landscape. The motion of the local group today carries a record of that history. Our velocity was not created suddenly by one recent encounter. It accumulated as the surrounding universe evolved. The Great Attractor region became denser over time, while nearby voids lost matter to their boundaries. The imbalance strengthened and galaxies responded. Even now, the response continues. The Sun circles within the Milky Way while the Milky Way moves with the local group. The local group follows a flow shaped partly by structures that began forming before Earth existed, before the Sun formed, and before the Milky Way acquired its present spiral shape. At this scale, gravity acts without hurry. A cluster does not need to pull strongly during one human lifetime. Its influence persists across eras. A tiny acceleration, maintained for millions of years, changes the path of an entire galaxy. There is no sensation of this force in the room. Local gravity is dominated by Earth, the Sun, and the Milky Way. The contribution from a cluster hundreds of millions of light years away is exceedingly small at any given moment. Yet the Milky Way has had cosmic time in which to respond to the wider field. Time turns the nearly imperceptible into motion. The invisible framework around the Great Attractor does not announce itself with light. It is present in orbital speeds, hot gas, lensing patterns, and the collective drift of galaxies. The stars show where some matter has settled. Gravity reveals how much more remains unseen. The motion of the Milky Way is shaped not only by what lies ahead, it is also shaped by what is missing behind and beside us. This is one of the less intuitive parts of the local cosmic flow. Dense regions attract matter. That is familiar enough, but an underdense region can also influence motion, not by pushing, but by failing to provide an equal pull in the opposite direction. The result is an imbalance. Near the local group lies a large region containing fewer galaxies than the cosmic average. It is known as the local void. Its boundary passes surprisingly close to our galactic neighborhood, while its interior extends across tens of millions of light years. The local void is not completely empty. A few faint galaxies occupy parts of it. Thin gas may be present. Dark matter is not absent in an absolute sense. But compared with the filaments, groups, and clusters around it, the region contains much less matter. That difference matters. Imagine a small object placed between two distant crowds. If the crowds contain equal mass and stand at equal distances, their gravitational pulls can partly balance. If one crowd thins or disappears, the pull from the other side remains. The object accelerates toward the denser direction. Nothing in the emptier region has pushed it away. The missing mass has simply failed to oppose the attraction from elsewhere. The local group appears to participate in a motion of this kind. Part of our velocity carries us away from the local void and toward denser structures connected with Virgo, the Great Attractor region, and more distant concentrations. The full motion cannot be divided perfectly into one cause at a time, but studies of the local velocity field suggest that the void contributes meaningfully to the direction we travel. This helps explain why the Milky Way's path is not aimed neatly at one cluster. The flow is the combined result of attraction and imbalance. Matter ahead draws us. Reduced matter elsewhere leaves that attraction less opposed. The geometry changes with position, so neighboring galaxies do not all move along identical lines. A galaxy close to a filament may be guided partly along it. A galaxy near a void boundary may move outward from the underdense region. A group embedded in a cluster feels the cluster's local gravity more strongly than the distant landscape. The cosmic web is not a single current. It is a field of many currents layered across one another. Voids are central to that field. They occupy most of the volume of the observable universe. The galaxies, clusters, and filaments that dominate astronomical images are concentrated into a smaller portion of space, arranged around broad underdense interiors. In a map of the cosmic web, bright structures often resemble threads surrounding dark cells. Those dark cells are not merely spaces left over after everything important has been counted. They are active parts of structure formation. Their expansion helps move matter towards surrounding walls and filaments. Their low density changes the gravitational field around them. Their boundaries help define where galaxies collect. A void begins with a small shortage of matter. In the early universe, density varied only slightly from one region to another. Where matter was somewhat more abundant, gravity gathered more of it. Where it was somewhat less abundant, nearby overdense regions pulled material away. The difference grew with time. Dense regions became denser. Underdense regions became emptier. As the universe expanded, voids enlarged more rapidly than crowded regions because they contained less gravity to slow their local expansion. Matter migrated toward their edges, where filaments and walls became more pronounced. The present cosmic web emerged from both sides of this process. Clusters are shaped by accumulation, voids are shaped by evacuation. The Great Attractor region cannot be understood fully without the emptier spaces around it. A gravitational basin is defined by the space's slopes, and those slopes depend on where matter is concentrated and where it is scarce. The local void helps tilt the local terrain toward Virgo and the larger structures beyond. Farther away, other voids contribute to other flows. Each one changes the balance across its neighborhood. Galaxies near their boundaries tend to move toward denser walls. Clusters grow where several filaments meet. Large-scale motion becomes the result of many underdense and overdense regions arranged together. This view replaces the image of a universe filled with separate objects floating in neutral emptiness. The emptiness is not neutral. It has shape, scale, and consequence. Astronomers map voids using the galaxies around them. A region with very few detected galaxies may be a true void, but observational limits must be considered. Faint galaxies can be missed. Dust may obscure part of the sky. A survey may not reach deeply enough. Researchers therefore combine galaxy catalogues with velocity reconstructions and statistical models to estimate the location and depth of underdense regions. The local void is particularly difficult because part of it lies near the plane of the Milky Way. Once again, our own galaxy interferes with the wider map. Radio observations help find hydrogen-rich galaxies behind the foreground. Infrared surveys reveal systems hidden by dust. Distance measurements show whether galaxies near the apparent edge belong to the void boundary or merely overlap with it in the sky. The map improves slowly. Some sections of the boundary are better known than others. The void may contain smaller substructures rather than one uniform interior. Its exact dimensions depend partly on how underdensity is defined and on which survey is used. The general influence, however, remains important. The local group is not situated in the center of a crowded cosmic region. It lies near the edge of emptier space, connected by nearby filaments to denser structures. This location helps explain why our motion contains both an approach toward mass and a departure from underdensity. There is a useful calmness in this arrangement. The word void can suggest absolute nothingness, but cosmic voids are not places where reality has ended. Space continues through them. Light crosses them. Gravity remains. A few galaxies may persist inside. Dark energy and the expansion of the universe act there as they do elsewhere. What changes is density. A void is less a hole cut into the universe than a region where the universe has gathered less of itself. From within a void, the surrounding galaxies might appear concentrated toward distant walls. The nearest luminous neighbors could lie farther away than they do for us. The night sky from a small isolated galaxy might contain fewer nearby galaxies, though distant background light would still fill the larger cosmos. Inside the local group, our sky does not reveal this geometry directly. The Milky Way surrounds us with its own stars. Andromeda is visible under dark conditions. A few nearby galaxies can be detected with the unaided eye from suitable locations. The larger pattern requires telescopes and distance measurements. Human vision is not built to recognize underdensity across tens of millions of light years. It sees what emits enough light to arrive. Astronomy must also measure what is absent. This is a different kind of observation. To detect a cluster, astronomers count galaxies, measure hot gas, and study gravitational lensing. To detect a void, they must establish that a broad region contains fewer galaxies than expected. The evidence lies in scarcity, distribution, and motion. A blank area on a map may represent missing data, or it may represent a real feature of the universe. Distinguishing the two has been part of the work around the Great Attractor from the beginning. The zone of avoidance once looked empty because dust blocked the view. The local void looks sparse because it truly contains less matter. One absence belongs to observation, the other belongs to structure. Learning to separate them changed the map. It also changed the story of our motion. The Milky Way is not simply being drawn forward by a hidden concentration. It is moving through a field in which crowded regions and empty regions shape the path together. The local void helps carry us away from one side. Virgo, Norma, Shapley, and the intervening filaments help draw us toward another. The final direction emerges from the whole arrangement. There is no single force assigned to each name. Gravity adds continuously. Every region contributes according to its mass, distance, and geometry. The categories are tools for understanding a field that is physically continuous. Over deep time, this field has guided matter toward the web's brighter edges. Galaxies formed there, clusters deepened there, voids widened between them. The local group came to occupy one of those boundary regions, neither isolated in emptiness nor settled inside a great cluster. We live near a transition. On one side, the thinning interior of a void. On the other, the connected structures leading towards some of the densest regions in the nearby universe. The Milky Way moves between them, not because space has chosen a destination, but because matter was never distributed evenly. The crowded places pull. The emptier places leave room for that pull to prevail. The motion of the Milky Way can be measured, modeled, and divided into contributing parts. Its future is harder to describe. A velocity tells us how an object is moving now. It does not always reveal where that object will finally arrive. On the scale of galaxies and superclusters, the surrounding gravitational field changes as matter continues to move and the universe continues to expand. The local group is traveling relative to the cosmic microwave background. Part of that motion is associated with nearby structures. Part reflects the Great Attractor region. Part is linked to more distant concentrations, such as Shapley. Part is connected to the uneven pull created by neighboring voids. But none of these influences acts on a fixed background. Virgo is moving, Norma is moving, Shapley is moving. The filaments between them continue evolving, while the space across the largest distances continues to expand. This means the Great Attractor is not a stationary destination waiting for the Milky Way to cross some final distance. It is a name for part of a gravitational pattern in the present universe. Within smaller systems, the future can be predicted more directly. Earth remains bound to the Sun because the Sun's gravity dominates over cosmic expansion on the scale of the solar system. The stars of the Milky Way remain bound to the galaxy. The Milky Way and Andromeda remain part of the same gravitationally connected group. Their mutual approach is local. The local group is dense enough that its internal gravity overwhelms the general expansion between its members. Over several billion years, the Milky Way and Andromeda are expected to interact, alter one another's structures, and eventually form a larger merged galaxy. That event will occur within the local group's own gravitational history. It does not require the group to reach Virgo, Norma, or the center of the Laniakea flow basin. Across greater distances, the balance changes. Galaxy clusters can remain bound. Closely connected groups can continue interacting. But superclusters are often too extended to collapse as single systems. The expansion of the universe separates many of their regions faster than gravity can draw them together. Dark energy is the name given to the component associated with this accelerating expansion. Its physical nature remains uncertain. The observational effect is clearer. On sufficiently large scales, the expansion of the universe has been speeding up rather than slowing down. This acceleration reshapes the meaning of every large-scale flow map. A map, such as Laniakea, records how galaxies move after the broad expansion is removed from their measured velocities. It shows a local gravitational pattern, yet the entire region does not necessarily share a future in which all its galaxies gather near the Great Attractor. some may continue toward denser structures for a long time. Others may remain bound only within their own groups or clusters. Still, others may be carried beyond practical contact as the space between large structures expands. The present flow and the distant future are related, but they are not identical. This is why the boundary of Laniakea should not be imagined as the outer edge of a permanent cosmic object. It is a watershed in a reconstructed velocity field. The galaxies inside it share a pattern of motion now. Over deep time, the changing balance between gravity and expansion will determine which connections persist. The Great Attractor region itself is not immune to this distinction. The Norma Cluster is gravitationally bound. Its galaxies remain within a common potential well, though they move, interact, and merge. Nearby groups may eventually join it if they are close enough and moving appropriately. But the Shapley Concentration lies much farther away. Its gravity contributes to the motion of our wider neighborhood, yet that does not mean the local group will one day arrive there. A distant mass can influence a path without becoming the path's final endpoint. Gravity reaches across space. Arrival requires more. It requires enough attraction, enough time, and a surrounding expansion that does not separate the regions too quickly. In the future universe, bound structures will become increasingly isolated from one another. The local group may eventually settle into one large galaxy, surrounded by its remaining companions and remnants. Other galaxy groups and clusters will undergo their own internal evolution. Across immense distances, accelerating expansion will carry unbound systems farther apart. Light from the most distant galaxies will become increasingly redshifted. Some galaxies visible to astronomers today will eventually pass beyond a horizon from which signals emitted later can never reach the descendants of the local group. The observable universe of the distant future may contain fewer external galaxies. Even though the universe itself contains no fewer structures, the night sky will change gradually, not during a human life, not during the span of recorded civilization, but across timescales far longer than the age of the sun today. The wider cosmic web will become less accessible to any observers remaining within our bound region. The Great Attractor will then belong partly to history. Its influence will have helped shape the velocity inherited by the local group. Its clusters and filaments will have participated in the nearby universe of our era. But the concept may no longer describe an active shared flow in the same way. Cosmic structures have lifetimes as ideas. A constellation exists because stars happen to align from one location during one period. A supercluster boundary exists because galaxies follow a measurable flow in one phase of cosmic evolution. A gravitational basin can be meaningful without being permanent. This does not reduce its reality. A river is real, even though its course changes. A coastline is real, even though tides, erosion, and rising water alter it. Laniakea is real as a description of the present gravitational landscape, while its exact boundaries and long-term fate remain dependent on time. The same is true of the Great Attractor. Its name preserves a stage in astronomy, when a common galactic motion was detected before the hidden structures were fully mapped. Later observations revealed Norma, the surrounding filaments, the contribution of Shapley, and the role of nearby voids. Future maps may refine the picture again. Larger distance catalogues will reduce uncertainty. New surveys will measure millions of galaxies more precisely. Radio observations will continue filling the regions behind the Milky Way. Infrared telescopes will identify obscured galaxies. X-ray observatories will trace hot cluster gas. Gravitational lensing surveys will improve estimates of unseen mass. The motion of galaxies may be reconstructed across a volume far larger than the one used to define Laniakea. As that map expands, some familiar boundaries may shift. The Great Attractor will not vanish from astronomical history, but its place within the full flow may become more carefully defined. It may be understood less as the center of our motion and more as one major feature within a sequence of density fields extending across the nearby universe. This is how a scientific mystery often changes. It does not always end with one object being found. Sometimes the question becomes larger than the original answer. Astronomers asked what was pulling the Milky Way. They found that Virgo mattered, but was not enough. They found the hidden concentration near Norma, but it was not enough. They found Shapley farther away. They found the local void on another side. They found that the full velocity arose from the sum of many structures rather than from one concealed source. The mystery became a map, and the map became a study of how uneven matter creates motion across the cosmic web. There is a present moment anchor within this future. The Milky Way is moving now, but nothing nearby is being torn from its place by that motion. Earth remains in orbit. The Moon continues around Earth. The solar system remains inside the galaxy. The local group carries its members together through the larger field. A shared velocity does not disturb the relationships contained within it. You can rest inside many motions because the surrounding world shares them. Earth turns, yet the room turns with it. Earth follows the sun, yet the atmosphere and oceans follow too. The sun crosses the galaxy, carrying its planets. The Milky Way moves with the local group. At each scale, the motion becomes noticeable only against a more distant reference. This nesting of movement continues outward until the familiar idea of being still becomes difficult to preserve. Stillness is always local. It is a relationship between nearby things traveling together. Against Earth, the body can be still. Against the sun, Earth is moving. Against the galaxy, the sun is moving. Against the cosmic microwave background, the local group is moving. No one description cancels the others. They belong to different scales. The Great Attractor belongs to the largest of these everyday unseen motions. It reminds us that a galaxy can participate in a journey without containing any observer capable of feeling the acceleration. The influence is distributed. The timescale is immense. The movement is shared. Long before the sun formed, matter in the nearby universe had already begun gathering into the structures that would shape this flow. Long after the sun is gone, some consequences of that distribution will remain written into the paths of galaxies, but the map will continue changing. Some structures will merge, some will separate, some will pass beyond observation. The gravitational landscape of the present is neither the beginning nor the final arrangement. It is one frame in a much longer evolution. For now, the Milky Way moves toward the denser southern regions of our local map, while the local void recedes behind and the flow and Shapley adds its distant influence. The direction can be measured. The final destination cannot be named so simply. The Great Attractor began as a name for an absence. Astronomers could see galaxies moving, but they could not yet see enough of the matter guiding them. The motion appeared first. The structure came later. That order is common in astronomy. A planet can be inferred from the movement of another world. A black hole can be recognized through the orbit of a nearby star. Dark matter can be mapped through the bending of light. In each case, gravity reveals form before light completes the picture. The Great Attractor belongs to the same tradition. Its influence was written into the peculiar velocities of galaxies scattered across the nearby universe. The local group carried part of that signal. The cosmic microwave background provided a distant reference. Surveys showed a shared drift toward the southern sky. Then the hidden region began to open. Infrared observations reached through the dust. Radio telescopes found hydrogen-rich galaxies behind the plane of the Milky Way. X-ray instruments revealed hot gas inside massive clusters. The Norma Cluster emerged as one of the densest visible landmarks near the center of the flow. Farther beyond it, the Shapley Concentration widened the gravitational context. Closer to home, the local void showed that motion was also shaped by missing matter. Laniakea gathered many of these discoveries into a single map of converging galaxy paths. The original mystery did not disappear. It changed scale. The hidden force moving the Milky Way is not one object concealed behind the stars. It is the combined gravity of an uneven universe. Clusters contribute, filaments contribute, dark matter contributes. Voids alter the balance. Distant concentrations add their influence across space. The Milky Way responds to all of them at once. This answer is less dramatic than a single cosmic engine, but it is more complete. It replaces a point with a landscape and a destination with a flow. the flow can be measured more precisely each year. New galaxy surveys are expanding the map of the nearby universe. Better distance measurements reduce the uncertainty in peculiar velocities. Radio observations continue to reveal galaxies hidden behind the Milky Way. Infrared detectors separate distant systems from crowded foreground stars. Future maps will contain more detail than the first Great Attractor studies could have imagined. They may refine the boundaries of Laniakea. They may show how much of our motion arises from nearby structure and how much comes from farther concentrations. They may trace the influence of underdense regions more clearly. They may reveal hidden groups and filaments still missing from current catalogues. The broad picture is unlikely to return to simplicity. The more deeply the local universe is mapped, the more connected it becomes. A galaxy cluster is not an isolated mountain in empty space. It sits where filaments meet. Those filaments connect to other clusters. Voids curve around them. Dark matter extends through the entire arrangement. Gravity responds to the whole distribution. The Milky Way is one moving point within that field. It carries several 100 billion stars, clouds of gas and dust, stellar remnants, planets, moons, and the small region where this question is being considered now. None of those contents need to know the direction of the larger motion. The galaxy travels as one system. A star born on one side of the Milky Way shares the same broad cosmic drift as a star born on the other. A planet forming inside a distant molecular cloud inherits the motion of the galaxy before it completes its first orbit around its sun. The motion enters every local story without changing its local form. Stars still orbit the galactic center. Gas still gathers into clouds. Planets still follow their stars. The Great Attractor adds another layer beneath all of them. It is a reminder that no system is completely separate from the structure surrounding it. The Milky Way has its own gravity, shape, and internal history. Yet its path through space is influenced by matter far beyond its spiral arms. The local group has its own future, but it also moves within a larger field. Laniakea describes a shared flow, while the expansion of the universe ensures that not every shared motion leads to a shared final home. Each scale contains both independence and connection. The solar system is bound to the Sun. The Sun is bound to the Milky Way. The Milky Way is bound within the local group. Beyond that, the relationships become broader and less permanent, but they do not become meaningless. Gravity continues across the widening distances. The name Great Attractor may remain even as its scientific meaning becomes more precise. Names often preserve the stage at which a question first became visible. They carry the uncertainty of their beginning into the clarity that follows. The Great Attractor sounds like a hidden object because that is how the mystery first appeared. Galaxies moved as though something lay beyond the Milky Way's crowded plain. The later answer did not remove the name. It placed the name inside a larger understanding. There is a dense region near Norma. There is a broader flow basin across Laniakea. There is a more distant mass concentration at Shapley. There are nearby voids changing the balance. There is dark matter shaping the web without producing light. And there is the expansion of the universe carrying unbound structures apart, even while local gravity bends their paths. All of these statements can be true together. The Milky Way is moving toward a denser region without being destined to arrive at a fixed point. It is responding to matter without being pulled by one object. It belongs to a supercluster flow, without every part of that supercluster being permanently bound. The universe allows several scales of description to overlap. This is why the original question has no single final arrow. Where is the Milky Way going? Toward Andromeda on the scale of the local group, around its own center on the scale of the galaxy, toward the Great Attractor region within the nearby velocity field, along a larger motion influenced by Shapley and neighboring voids, and outward with the changing geometry of the universe on scales where expansion dominates. Each answer is measured against a different frame. Together, they describe the full movement more honestly than any one direction could. The night sky does not display these vectors. It offers stars, planets, a pale band of galactic light, and the dark intervals between them. The motion remains beneath appearance. Yet every photon arriving from beyond the Milky Way carries information from the structure through which it traveled. Every redshift places a galaxy within the expansion. Every peculiar velocity reveals a departure. Every distorted image marks the presence of mass. The map is built from these small signs. No observer sees the whole flow directly. Astronomy assembles it piece by piece, from light, motion, distance, and time. The result is not a photograph of a hidden force. It is a reconstruction of relationship. The Milky Way moves because other matter exists where it does, because less matter exists elsewhere, and because those differences have acted across billions of years. There is no sound in that motion. No wake forms behind the galaxy. No edge of space passes across the stars. The local group continues through the cosmic web while its internal worlds follow their nearer paths. And beyond the plane of the Milky Way, the gravitational landscape remains ahead, guiding the galaxy through a direction no eye can see. The stars travel with us,